Good morning, my dear students. Now, welcome back to our optical system course. It's lecture number 4, optical cavity. It's the second part of this lecture. We consumed the previous week, if you remember, on understanding what is meant by an optical cavity. Today, I will start with a very quick review about what we did in the first part, and then I will terminate this lecture by describing two new concepts. First, what's called the photon lifetime, and second, what's called the optical cavity under gain. Now, let's start our lecture. First, if you remember, we start with the definition of an optical cavity, and we taken as an example of a 1D optical cavity consisting of two mirrors, as you can see, one on the right and one on the left. We have an electromagnetic wave in the form of a photon that's propagating this optical cavity through a series of reflections, as you can see here. We define the electromagnetic field just inside the optical cavity by the term E naught, and then we start to write an equation to describe the electromagnetic field at different points just after the reflection from the first mirror or the second mirror actually, and then here after one round trip and so on. We start with considering this very important condition, which is the condition for maximizing the electromagnetic field inside the cavity. We did so through saying that 2kd, where k is the propagation constant, equals 2 pi over lambda, and d is the distance between the two mirrors, equals to q times 2 pi. Q is an integer that theoretically can start from 0. However, when q is equal to 0, that means that d equals to 0, which has no physical meaning. That means that the distance between two mirrors is equal to 0, which means that there is no cavity at all. Then we go to, or we reach this definition that d, which is the distance between the two cavities, should be an integer multiple of lambda naught, which is the wavelength of the photon in vacuum or in free space, over 2 pi. This is the distance you should adjust your optical cavity in order to make a maximum electromagnetic field inside the optical cavity. Then we define the mu term, which is a frequency. We're using the same equation by the q is a multiple integer of c, speed of light, over 2 n d, where n is the refractive index of the material used inside the cavity. And from here, we determine what's called the free spectral range, which is the distance between any two successive frequencies. If you put first q equal 1, you will have the first resonance at c over 2 and d. If you put q equals 2, you have c over 2c over 2 and d. Then the distance between these two frequencies is basically the free spectral range, or what's called delta mu, which is equal to c over 2 n. Then we turn to determine the total electrical field inside the cavity. First, we determine the total electric field coming from mirror number 1, which is simply the summation of all these terms: E naught, E1 plus, E2 plus, and so on. And using mathematical Taylor series, we reach this finite form that's E total plus equals to E naught over 1 minus gamma 1 gamma 2 e power minus j k2d, where please remember that gamma 1 and gamma 2 are the reflection coefficient for the mirror number 1 and the mirror number 2. Using the same equation, using the same procedure, we reach an equation for the intensity of the total intensity inside the electrical field, inside the optical cavity, and then we use this intensity, but we write this intensity now not in terms of gamma, in terms of r, where r is simply gamma squared. And as we mentioned in the lecture, gamma is the reflection coefficient in terms of electrical field, and r is the reflection coefficient in terms of power, or what is usually we call in optics as the intensity. Using all these mathematical expressions, and by somehow long mathematical derivation, we made it together in the previous lecture. We reach this very important equation. This important equation represents the total transmission on the optical cavity. Again, the definition of the transmission is what or the amount of energy transmitted from the cavity. I mean here in this left hand side, in this right hand side, the amount of intensity transmitted here over the amount of intensity inside the optical cavity or incident to the optical cavity on the left hand side. So I transmitted over I incident equals to what we call the transmission term. Here is the transmission term. As you can see, the transmission term is a function on the reflection coefficient of each mirror R1 and R2, and is also function in the propagation coefficient K, 2 pi n over lambda node, and also the distance between the two mirrors. Now, what about the conditions of T? We first start to make this equation a bit simpler, and we say that what if R1 is equal to R2 equals to R, and then we start to seek for a condition for maximum. If you put R1 equals to R2 equals to R, then simply you will find 1 minus R squared on the denominator. And here again, 1 minus R squared on the denominator plus 4R sine square KD. So in order to maximize this term, basically the maximum transmission is equal to 1. Then you have to make this term is equal to 0. Or simply you have to make this sinusoidal term equal to 0. In order to make KD equal to 0, then simply the condition will be KD should be equals to Q pi. So if KD is equals to Q pi, these transmission terms will tend to 1. Again, as we remember, this condition was already settled in the first step in our optical cavity when we say that 2KD equal Q2 pi. So if we apply this condition, we will reach T equals to 1 if and only if R1 is equals to R2. Okay, now this is the condition when R1 is equals to R2 and KD is equals to Q pi. This is a maximum condition. Based on this equation also, we reach a very important equation. This equation, if you remember, also we did the mathematical derivation that the intensity inside the optical cavity equals to the intensity incident to the optical cavity over 1 minus R2, where R2 is the reflection of the second mirror. Why this equation is very important? Because basically, as you know, the reflection of mirrors are relatively high number. For example, you can say that R2 is equal to 99%. You have a reflection coefficient or reflection intensity reflection of 99%. Then simply if you substitute here by 0.99, that means that I plus equals to IN, which is incident, over 1 minus 0.99. 1 minus 0.99 is 0.01. Here again, I plus, or the total electric intensity of photons inside the cavity equal to the incident photon over 0.11, which means that what is inside the cavity is 100 times greater than what is outside. Then, based on this equation, you are capable of magnifying the intensity of the photon 100 times inside the optical cavity. Okay, what about if this resistance is 99.99%, for example? Then the intensity inside the cavity will be 10 power 4 or 10,000 higher than the intensity. So that's why the lasers come from. How you can excite a huge amount of light intensity using a very small amount of light. Maybe this small amount of light is simply some noise. How you can make a very huge or a very large signal or a very large intensity of photons inside the cavity using some unwanted noise. This is a very important equation. Now we go to plot the transmission curve. As you can see, the maximum of transmission is basically equal to 1. This is the transmission axis, and usually for the y-axis you can plot it either versus Q, as you can see here, where you will find the resonance according to the integers. As you can see, Q equals 0, Q equal 1, blah 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 blah. This is a very important graph. Also, you can plot the same graph with an x-axis equal to frequency. You can plot the same graph with an x-axis equal to wavelength. You can find these transmission curves everywhere with an Q, wavelength, or a frequency x-axis. Now we turn to a second or the final stage on the previous lecture where we define again. Please remember that here we are just briefing what we say or what we said actually in the previous lecture, and it's not something new for you. It should be, so that's why I'm going too fast. Just a briefing for what we did in the previous lecture. So now here we have the term Q, or what's called the quality factor. Actually, this quality factor is defined not only in optics, it is defined in microwave resonance, in waveguides, in antennas, and all these stuff. The quality factor actually is a parameter that describes what's called the sharpness of the signal. So here, as you can see, it's a ratio between the resonance frequency, mu node, and the delta mu. Please take care that this delta mu is a bit different to the first one we defined. The first one we defined was the free spectral range, which is the distance between two successive frequencies. However, this delta mu is what's called the full width at half maximum, or what you know initially in communication as the 3 dB bandwidth. So simply you go here to the maximum of the signal, then you divide it by 2, then you go to determine this width, the width of full width at half maximum. That's why we call it FWHM. So full width at half maximum, or delta mu, is this term. Of course, you are not asked to memorize this term at all, but you have to know the physical meaning of the sharpness of the signal. So when this delta mu stands to 0, this Q stands to infinity, which is actually what we can call the hypothetical ideal laser. If you remember, ideal lasers is represented by a delta Dirac function where the delta mu, or the full width at half maximum, is equals or tends to 0. So as far as you have a higher Q, you have a higher sharp, or a better signal in the respect of sharpness. It's a sharper signal as far as you have a higher Q. Finally, we define a term which called the fence. The fence is simply the ratio between the free spectral range and the full width at half maximum. So you can easily describe it in this graph. This is the full width at half maximum, the distance between two successive frequencies. And this is the full width at half maximum, which is the distance or the width of the signal, the 3 dB bandwidth. If you divide these two terms together, then you will get what's called the fence of the signal. And this is an expression for the fence. And again, you are not required, or you are not asked to memorize either the fence equation or the full width at half maximum equation, or the transmission equation. These three equations will be given to you in case you need it in the final exam or any type of assessment. Now, this is what we did in the previous lecture. Let's now turn to the second part of this lecture. Actually, it will be somehow a small part. We have only to define two new concepts. The first concept will be what's called the lifetime of the photon. Okay, let's start our journey in order to understand what's called the photon lifetime. This is the optical cavity. We have a mirror on the left hand side, we have a mirror on the right hand side. And photons, or basically electromagnetic waves, is propagating from the left to the right and from the right to the left using the reflection coefficients of these two mirrors, which is relatively high numbers because they are mirrors. Now, let's assume that we start our journey with NB number of photons. We have a total number of photons equals to NB. Now, when you reach this point, then this number of photons will be split. Some will be reflected back and some will be transmitted. Here we know a coefficient called R2. R2 represents the amount of intensity, which is number of photons per unit area per unit time. The intensity is simply, or here number of photons with or a certain portion of photons will be reflected. Sorry for this confusion. A certain number of photons will be reflected, and a certain number of photons will be transmitted. Based on our knowledge that we have a reflection coefficient called R2, then R2 of this NB will be reflected, and 1 minus R2 of this NB will be transmitted. So very simple. When we say that the reflection of this mirror is 95%, and I have here 100 photons. That means when this 100 photons reach this point, 95 of these photons will be reflected, and 5 of these photons will be transmitted. Very easy. Now we have R2 and B is propagating from the right to the left. Then we will reach this point. When we reach this point, then we have a reflection. The reflection now is R1. Then we will get R1, R2, and B. So that means when we start with NP photon, after one round trip, we will end with R1, R2 times NB photon. So what survives from this photon is R1, R2 from NB. For example, let's make it an easy example. If I start with 100 photon and then I have a reflection coefficient of 0.9 here and 0.9 there, then after one trip, here I will lose 10%, and here I will lose another 10%, then the total is 0.9, 0.9 times 100. So this is simply the surviving factor. Okay, so let's now try to make it in a mathematical form. And in order to make it like that, please permit me to switch the window into the lecture script. I believe in the lecture script you will have a better way to understand the mathematics. Okay, so try to make it larger a bit. Okay, so if we talk about the rate of surviving, or the amount of photons that escape from the optical cavity, we can say that dNB by dt. This dNB by dt is simply describing the rate you are losing photons with. The rate you are losing photons with. So it is simply equals to the total number of photons you lose in one cycle over the time of one cycle. So if I have, let's now say that S equals to R1 and times R2, and S here is what's called the surviving factor, then basically if S times NP will be survived after one round trip, then 1 minus S times NP will escape with round trip. So the number of photons, if here now we will consider that the photons that will escape from the optical cavity, that means that this photon is somehow died. So the number of died photons in one trip is 1 minus S times NP. And the time for one trip is T round trip. So simply dNP by dt is 1 minus S times NP, which is the number of photons escaped, or between quotation, died over the round trip cycle. Here we can define what's called the photon lifetime. We will consider the photon lifetime as the total round trip here over 1 minus S, where S is a surviving factor. And we will call this as the photon lifetime for our optical cavity. So very simple. Here, let's turn back to the to the slides. I will return again to the lecture script in a second, but let's now return back to the slides. Here we have 1 minus S again, which is the amount of photons escape here, which is amount of photons die, either dying here or there. So we have, for example, some photons will escape here, and some photons will escape there. Then this is the total number of died photons over the total number taken by one round trip. Then simply the tau p, or the photon lifetime, is TRT over 1 over S, which is the number of escape, which is the photon lifetime. Now we are going to integrate the definition of the photon lifetime with the quality factor. Here, actually, we have somehow a long mathematical division. I will not go into details about this mathematical division. However, you can find it here step by step, the mathematical division. But let's start first with the conceptual part or the physical meaning about how we will integrate the Q factor, which is again the measure for the sharpness of the signal, with the photon lifetime, which is tau p. Here we define the Q in another way. If you remember, few slides ago, we defined the Q as the ratio between, I think here, yes, as a ratio between the center frequency or the resonant frequency and what's called the full width at F max. And based on this mathematical division, we can easily understand that this is an evaluation for the sharpness of the signal. Now we'll start to define it in another way. We will say that Q equals to 2 pi times energy stored in the system at resonance, which is somehow mu naught, or energy lost in one over the energy lost in one cycle. So how we can understand this physical meaning? Again, Q is the measure of the sharpness of the signal. So what do mean that the signal is sharp is that you have a minimum losses. I mean that the energy lost in one cycle tends to be zero. So when the energy lost in this cycle, in one cycle, tends to be zero, this Q tends to infinity, which is the highest sharpness signal. All the photons you are propagating in the same frequency with a delta Dirac function. This is somehow the same like what we say here, if you remember that here, when we say that the full width at half maximum is equals to 0 or tends to 0 for a hypothetical laser. So in order to minimize the transmission, you will have to somehow, in order to minimize the losses, you will have a Q equals to infinity. Okay, so 2 pi times W is the energy stored in the system at resonance, over T, which is time for one cycle, times P, which is the power losses. You know that energy is equal to time power, or power times time. Okay, so 2 pi over T is simply what we can call omega naught, which is the angular frequency. 1 over T is the frequency, then 2 pi over T is the omega naught or angular frequency, and W over B is simply the energy stored in the system at resonance over the power loss per cycle. As I said, the power and the energy is related by a time relation. So easily you can replace this P by dW by dt. Then you will have dW by dt equal minus omega naught over Q times W. Here is a differential equation in terms of W. Okay, now let's turn to our definition. If you remember, we say that dNB by dt is equals to NP over tau p. This equation we just reached, if you remember, few slides ago in the photon lifetime. Here, if you remember, we reached this equation. So this is simply the same equation. We already reached it in the previous slide. And then we say that dW by dt, or the relation between the energy and the number of photons, is simply h mu, because you know that the energy of single photon is h mu. So if you have n photons, their energy will be h mu times n. Very simple. So this is the relation, and then we make this mathematical equality till we reach this equation that the tau p equals to Q over omega naught. Here is the integration, let me say, between the photon lifetime and the quality factor. You can say that the photon lifetime equals to the quality factor over omega naught, where omega naught is equals to the angular frequency at resonance, or you can say it's 2 pi mu naught, or 2 pi over T. This is a simple integration. Again, the mathematical step-by-step derivation is not required from your side. However, you have to memorize this equation, because sometimes you will need this equation in order to solve some problem. Now let's turn to the final part in our lecture. I will turn back to the slides if you permit me. Now we will turn to the final stage in our lecture, which is the cavity under gain. Okay, in order to understand this relation, let's now start to go to this famous equation, which is, I think here, yes, it's the transmission equation. This is the basic transmission equation we drive together in the previous lecture, and we make somehow a quick review about it in this lecture. If you remember, we reach this equation by assuming that we have two mirrors. These two mirrors have a distance between them equals to d. We have a reflections R1 and R2, and we have a propagation coefficient called 2k. That's why when the electromagnetic wave is propagating here, we multiply this by e power minus j k z, where z is the distance propagating. For one complete cycle, it becomes e power minus j k 2d. So this exponential term represents what we call the propagation coefficient associated to the electromagnetic wave. Now, what if this medium is not just a propagating medium? By the way, this type of mediums, you usually name it or call it in the microwave course previous semester as a lossless medium. I mean, it's a medium, there is no alpha, there is no attenuation, and you only have the term beta, or what we call here k, as the propagation coefficient. No losses occurs when the signal is propagating in this medium. So it's a lossless medium. Now, it can be a lossy medium, that's true, when you will have the term alpha, and actually we will discuss that in the next lecture. But in the previous lecture, we defined a third type of materials, what we can call a gaining material. What do we mean by a gaining material? Let me try to find the previous lecture. I hope I can find it easy now. I don't need Excel anymore. Here, okay. So I think it's called atomic radiation. Okay. This was the previous lecture, my dear student. If you remember in this lecture, we make this experiment. Yes, it's here. Yeah, that's perfect. This is that. Sorry, there's a bit delay. Okay. So this was the experiment, if you remember. Yeah, here, this is experiment. This experiment was implemented by a source of light with a certain, actually it's a laser source. Then you have a material, and then you have a detector. And in this case, we say that we have three conditions, or three probabilities, if you remember. The first probability was that the total light incident to this system, or the total number of photons detected, equal to the total number of photons incident. Then it's simply just a propagating medium. There is no losses, there is no gain. This is actually what we typically did in our optical cavity. We just say that we have photons. When photon is propagating in the medium, there is no losses. It just had a phase change during the term e power minus j k d. That's all. There is a change in the propagation coefficient, but there is no losses. Another case, when the absorption term is dominating, if you remember, we will have what's called attenuation impact. I mean, the total number of photons detected is lower than the total number of photon incident. And here you should make, or here you should call this system as what we can call a losing system or an attenuating system. Here, using the perspective of microwave, you should add the term e power minus alpha z, which means that by going with distance z, you are losing some of the energy or you are losing some of the food. However, in our experiment, we reach a condition which we call the gain condition or condition for gain. If we apply this condition, then the number of photons will increase in the detector. Actually, I believe that you will never see this, or you didn't see this in the microwave course. Which now here we have what's called a gaining system. What we mean by a gaining system is that the total number of detected photons is greater than the total number of incident photons. That means that the system amplifies the number of photons. So let's now return to our optical cavity lecture. Okay, let's now return to our optical cavity lecture. Here, what if the medium here, the medium between the first reflecting glass and the second reflecting glass is a gaining medium. It's not a losing medium. It's not just a lossless propagating medium. It's a gaining medium. Now we have this transmission equation. What we will do simply is that we will add a term called G, where G represents the gain in the system. As you can see here, we have G node and we have G nodes. This G node associated with the propagation R1 and R2. So this G node represents the gain will be induced by the system. Here, the derivation of this equation is not required. It's actually simple. It's the same procedure we did the first one, but I will never ask you about this derivation. So you can just use this equation at least. Again, you are not asked to memorize the equation. If we need it, it will be given for you. But here is this G node represents the gain in the system. So simply, G node is an added number of photons. You increase the number of photons. So it's not only propagation. You are propagating and you are increasing what is inside. Okay, so the last question in this lecture actually is as follows. What if you put the gain equals to 1 over root R1, R2? What if you put the gain 1 over R1, R2? So what will happen? Let's see. If G equals 1 over root 1 R1, R2, then this will be simply will be equals to 1. You will have 1 minus 1 is equal to 0. Again, this term, you can get rid from this term if you put the maximum condition. I mean that KD equal Q pi, that this term will be 0. Then this transmission will reach to infinity. You have a denominator is equal to 0. Okay, we will discuss this later in the course. Just a question in order to brainstorm together this condition. We will not tackle it actually here in this lecture. We will tackle it later in the next lecture. Now we have completed the lecture, which is the optical cavity in 2 parts. We understand what's called an optical cavity, the definition of a 1D optical cavity. We reach that transmission equation and we know how we can, or what are the conditions needed to make the transmission is equal to 1. We have to make R1 is equal to R2, and we have to put also we have to put KD equal to Q pi. We also have studied some definitions like the field spectral range, like the full widths that have maximum, like the films, like the quality factor. Then in the second part, we understand what's called the lifetime, and we integrate the lifetime to the quality factor with the equations that Q equals to tau p times omega node, where omega node is the angular frequency of the medium, or angular frequency at resonance to pi mu node. And finally, we studied what's called the optical cavity under gain, and we excite and question regarding what if this gain equals to 1 over root R1 and R2, where the T will tend to infinity. This was the complete lecture for the optical cavity, my dear students. Now we have finalized this chapter. Then let's now see you in the next chapter, which is the laser oscillation and amplification. Thanks for your concentration.